Welcome to the video lecture of course code U18Esit404 Digital System Design. And I am Dr.B. Dhanalakshmi, Professor, Department of Information Technology, Bharat Institute of Higher Education and Research, delivering this lecture. And today we are going to see about topic combinational circuits in Unit 2. And first we will start with the introduction of circuits. That digital system consists of two types of circuits, namely combinational circuits and sequential circuits. And sequential logic circuit comprises both logic gates and also the state of the storage elements such as flip-flops, latches, etc. As a consequence, the output of a sequential circuit depends not only on the present value of the inputs but also on the past state of the inputs. So here they have the memory element to store the past state of the inputs. And now we will see about our subject topic combinational circuit. Combinational circuit generally consists of logic gates whose output at any time is determined from the present combination of inputs. So the logic gate here is the most basic building block of the combinational logic circuits. The logical function performed by a combinational circuit is completely defined by a set of Boolean expressions. And the combinational circuit consists of input variables, logic gates, and output variables. A combinational circuit even consists of the signals from input, that is input signal and output signals that are generated according to the logic circuits which are involved in it. And binary information collected from the given data is transformed to the desired output data in this process. And both input and output are here considered as the binary signals. That is, both the input and the output signals are of two possible states, logic 1 and logic 0. And here is a block diagram of a combinational logic circuit. So here we can see the n input variables which are sent from the input side, and we can get m output variables at the destination end. For n number of input variables to a combinational circuit, then 2 power n possible combinations of binary input states are possible. For each possible combination, there is one and only one possible output combination. A combinational logic circuit can be described by m Boolean functions, and here each output can be expressed in terms of n input variables. And now we will see the design procedure of the combinational circuit. Any combinational circuit can be designed by the following steps. First, we have to identify the problem, and the problem stated should be clearly understood. And second step, we have to identify the input and the output variables involved in the problem. And third step is the input and the output variables are assigned with letter symbols. And now we will see the construction of the truth table to meet the input and the output requirements. And then we have to write the Boolean expression for various output variables involving the input variables. Then this Boolean expression should be simplified using any method of minimization like algebraic method, K-map method, or tabulation method. A logic diagram then is realized from the simplified Boolean expression using logic gates. And here are the guidelines that should be followed while choosing the preferred form for hardware implementation. The first guideline is that the implementation should have the minimum number of gates, with the gates used having the minimum number of inputs. And the second guideline is that there should be a minimum number of interconnections. and the limitations on the driving capability of the gates should not be ignored at any case. And now we will see the basic building blocks involved in the arithmetic circuits. Here, the basic building blocks that form the basis of all hardware which are used to perform the arithmetic operations on binary numbers. Some of the building blocks mentioned here are half adder, full adder, half subtractor, and full subtractor. We can even involve multiplexer, encoder, decoder, and so on. And now we will see about the half adder circuit. A half adder is a combinational circuit that can be used to add two binary bits. And it has two inputs that represent the two bits to be added and two outputs, with one producing the sum output and the carry output. So this half adder involving two bits of input and two bits as the outputs. So outputs here will be the sum output of the addition result, and carry output will just produce the carry result of the addition result. And the block schematic diagram of the half adder is given on the slide. So here A and B are the inputs, the numbers to be added, which are in bits, and when added we get two outputs, one is sum and other is carry. And the truth table of the half adder circuit shows the possible input combinations and the corresponding outputs, and they are tabulated here. So under inputs we have input A and input B, where we have the combination of two bit values, that is 0 0 and 0 1, 1 0 and 1 1. And when we add 0 0, we get the sum result as 0 and carry as 0. And when we add 0 and 1, we get the sum result as 1 and carry result as 0. And when we add the two numbers A and B as 1 and 0, again we get the sum value as 1 and carry as 0. And when we add two ones, then we get sum as 0 and carry as 1. And the corresponding Boolean expression for the sum and the carry outputs are given here, which is stated like sum S is equal to A dash B plus AB dash, which is represented as A XOR B. And carry C is represented as product of A and B. And here is the K-map simplification of the given logic representation. The first one here represents the sum output, which is that of XOR gate, and the second one represents the carry output, which involves AND gate. The first one represents the sum output is that of XOR, and the second one here is the AND gate, and the logic diagram of the half order is sum S is equal to A XOR B, where we get the connection one input from A and another input from B for the AND gate and for the XOR gate. And here is the K-map reduction which has been done, where we get this expression sum is equal to AB dash plus A dash B, and which can be represented as A XOR B, and carry can be represented as product of A and B. And here is the full adder circuit, where the full adder is a combinational circuit that forms the arithmetic sum of three input bits. When compared to half adder involves two bits of inputs and full adder involves three input bits. It consists of three inputs and two outputs, where three inputs involve the two numbers to be added and the third input bit is the carry bit. So here the significant bits to be added are the two of the input variables, which can be seen in the schematic diagram of the full adder, where A and B represent the significant bits to be added, and the third input Cin represents the carry from the previous lower significant position. The full adder circuit overcomes the limitation of the half adder, which can be used to add only 2 bits. As there are 3 input variables here, 8 different input combinations are possible here in full adder. The truth table here can clearly explain that there are 3 possible inputs of A, input B, and the carry Cin, where we have the combinations of 3 bits of zeros and ones as 000, and the second input 001, where we get the carry as 0 and sum as 1, and the third input 010, where you get the sum result as 1 and the carry as 0. And when the fourth input, fourth sample 011, where we get the sum value as 0 and carry value as 1. And the next input here is 100, where the sum is 1 and the carry is 0. And the next input 101, where the sum here is 0 and carry value is 1. And next is 110, where the sum value is 0 and the carry value is 1. And at last, triple one, that is A value as 1, B value as 1, and carry value as 1. And when you add, the sum value you get as 1 and carry value you get as 1. And to derive the simplified Boolean expression from the truth table, the K-map method is adopted here, where we get, after simplification, we get the carry C out value as AB plus AC in plus BC in. And the sum S can be expressed as A dash B dash C in plus A dash B C dash in plus AB dash C dash in plus AB C in. And the Boolean expressions for the sum and carry outputs here is a simplified Boolean expression applying the K-map method. And here is the logic diagram for the full adder. So this denotes the implementation of the full adder in sum of products form. So here the first diagram, it involves 4 AND gates and 1 OR gate, and this right hand side diagram involves 3 AND gates and 1 OR gate. And here the implementation of full adder is shown involving 2 half adders and an OR gate. So you can see here the A input and B input are given to the XOR gate, and to find the sum value we are using one more XOR gate. So we involve 2 XOR gate in finding out sum, and in finding out carry we involve AND gate and OR gate. And here is the half subtractor circuit. So half subtractor is a combinational circuit that can be used to subtract one binary digit from another, and which produce a difference output and a borrow output. And here A and B are the 2 inputs, and which as a result gives the difference D value and the borrow B out value. And the truth table of the half subtractor shows all possible input combination and the corresponding outputs which are given here. So A, B with 2-bit data, which involves the combinations like 0, 0, for which we get the difference as 0 and borrow 0. And second input combination 0, 1, where the difference is 1 and borrow is 1. And third input set AB, where the inputs are 1 and 0, and where it shows the difference as 1 and borrow as 0. And last input category with A input as 1 and B input as 1, and which shows the output difference value as 0 and borrow as 0. And here is the logic implementation of half subtractor. So here, to find the difference, XOR gate is involved, and to find the borrow, we have the AND gate. So input A and B are supplied to the XOR gate and the AND gate. And here, while finding out borrow, we invert the A value and then we apply it to the AND gate. And now we will see about the full subtractor. So a full subtractor performs subtraction operation on 2 bits. So first bit is called a minuend and a subtrahend, and also takes into consideration where it has already been borrowed by the previous adjacent lower minuend bit or not. So here A, B are the 2 bits input data and B in is the borrow, and outputs are 2 bits where one bit is here for difference and the other is for borrow out. As a result, there are 3 bits to be handled at the input of a full subtractor, namely the 2 bits to be subtracted and a borrow bit is designated as B in. And we have 2 outputs, namely difference D output bit and the borrow output BO bit. And borrow output bit tells whether the minuend bit needs to borrow a 1 from the next possible higher minuend bit. So the truth table for the full subtractor is given here. Since 3 input bits are involved, we have the combination of 3 bits in the form of zeros and ones, where we have the inputs like A0, B0 and B in 0. In that case, the difference value we get is 0 and borrow is not required here. So borrow is also 0 here. And next input is A value as 0, B value as 0 and B in value as 1. And here, when we subtract, the difference value here we get is 1, borrowing 1. So the output value is 1. And the third input here is 0 for A value and B value is 1 and B in value is 0. And where here the difference D in the output is 1 and the borrow output value is also 1. And here when we subtract 0 value for A and B value as 1 and B in value as 1, in that case the difference value here is 0 and the borrow value is 1. And next input case for 100, the difference value is 1 and the borrow output value is 0. And next input is 101 where the difference value is 0 and the borrow value is also 0. And next input 110, that is A value as 1, B value as 1 and borrow input value as 0. Here the difference D we get as in the output is 0 and the borrow output value here is 0. And last input combination A value as 1, B value as 1 and borrow input value as 1. And here we get the output value for the difference is 1 and the borrow output value as 1. And here is the K-map simplification for full subtractor. So here the difference D is given by A dash B dash bin plus A dash B B dash in plus AB dash B dash in plus AB B in. So the borrow output simplified expression is given as borrow B out is equal to A dash B plus A dash B input value, borrow input value plus B in. So the Boolean expression for the difference and the borrow outputs after K-map simplification is given here. And here is the logic diagram for the full subtractor. And here To find the difference output value, we involve 4 AND gates, where the first AND gate involves A dash, B dash, B in. So this logic, we take it from the K-map simplification. See the first expression? So here A dash, B dash, bin. So here the first AND gate involves A dash, B dash, B in. And the second AND gate involves, can you see the second part of the expression where A dash B, B dash input borrow is given. In the same way here, the second AND gate get the input as A dash, then borrow B and B dash in. And the third AND gate takes the A, B dash and B dash in. And the fourth AND gate, so here the fourth part of the Boolean expression, simplified Boolean expression for the difference output D is A, B, B in, the borrow input. So here in the logic diagram, the last AND gate involves A, B and the borrow input. So when all these are then connected to the OR gate, where in the Boolean expression we use the plus operator, which means we are applying OR gate. So here this AND gate result will be connected to the OR gate, where any one of this AND gate result, if it is 1, then the difference value will be 1. And here on the right hand side is the logic diagram for finding the borrow output bit. So here 3 AND gates are involved and 1 OR gate is involved. And here the first AND gate involves A dash and B input, and the second AND gate involves A dash and the borrow input, and the third AND gate involves borrow and the borrow input, and which then are connected to the OR gate whose output is borrow out. And now we will see the implementation of the full adder in sum of products. The logic diagram of the full subtractor can also be implemented with 2 half subtractors and 1 OR gate. The difference D output from the second half subtractor involves the exclusive OR of the borrow input value and also the output of the first half subtractor. And here is the implementation result, where the difference D is given by borrow input value B in XOR when applied to A XOR B. So simplifying A XOR B, we get B input, borrow input XOR A XOR B can be expressed as A dash B plus AB dash. And then still simplifying, we get the difference D expression as A dash B B in dash plus AB dash B in dash plus AB B in plus A dash B dash B in. And here is the borrow output value, where it involves A dash B plus borrow input value and the product of A dash B plus AB dash the whole dash. And here when simplified, the borrow output value is given by A dash B plus B B input value plus A dash borrow input value. And here is the logic implementation of the full subtractor using 2 half subtractors and OR gate. And to find the difference value, we involve 2 XOR gates. And for finding the borrow output value, we involve the inverter gate, AND gate and OR gate. So this full subtractor involves the 3 input values, state A, minuend and B subtrahend and B in, which is borrow. So here the difference is mentioned here as XOR result by difference D, and then OR gate result as borrow output value. And here is the binary adder, that is parallel adder circuit, which is given here involving the full adder. So the 4-bit binary adder using full adder circuit is capable of adding two 4-bit numbers, which results in a 4-bit sum and a carry output, which is mentioned in the diagram. Like from the least significant bit, we are considering A0, B0, and A1, B1, A2, B2, and A3, B3, where A is one input number, B is one input number, and A input number involves A0 as the least significant bit, followed by A1, A2, and A3 as the most significant bit. And here, since it is the full adder circuit, it involves three input variables where A0, B0 are two inputs, and inclusive, we add up the carry input as the third input value. And the full adder circuit produces two output values. One is the sum value and other is the carry value. So the first full order circuit gives S naught as a sum value and C1 carry value will be transferred to the next full adder circuit. So next full adder circuit involves the bit A1, B1. So to A1, B1, we are going to add C1 also. So in that case, we get the sum result as S1 and carry result as C2. And here, the third full adder circuit involves A2, B2, and inclusive, we add up the carry which is received from the previous circuit, that is C2. And we get the two outputs which are S2 as the sum value and C3 as the carry value. And since it is a 4-bit counter, like 4-bit circuit, so we involve 4 full adder circuits where the most significant bit here involves A3 and B3, where C3 is also added and the result sum value is S3 and the C out value. And here is an example where we add the 4-bit words that is represented by A0, A1, A2, A3 form. The first number we are going to consider is 1111 and the second number B, which is expressed as B0, B1, B2 and B3. The number given here as B is 0011. So all the bits of organ and addend are fed into the adder circuits simultaneously and the additions in each position are taking place at the same time. And this is called as a parallel adder because we add each and every position of every individual numbers. And this example here, the organ word A involves 1111 and the addend word B involves 0011. And when we add A0 and B0, we get the sum result as 0 and the carry result as 1. And here the initial carry is considered as 0. And when we add up A1 and B1, along with which we are going to add the carry 1 also. So when we add the 3 bits, we get the sum result as 1 and again carry as 1. And here the carry value 1 is added with the A2 and B2 value where the resultant sum value is 0 and the carry value is 1 again. And again now when we add the two inputs carry A and B, that is A3 and B3. So here A3 is 1, B3 is 0. So when we add, we get 0 as the sum value and 1 as the carry value. And now we will see about multiplexer, where it is a combinational circuit with more than one input line, one output line, and more than one selection line. Here, this multiplexer selects binary information present from one of the many input lines, which depends on the logic status of selection inputs and routes it to the output line. And we always have 2 power n input lines for n selection lines whose bit combinations determine which input is selected. A multiplexer is also called a data selector since it selects one of many inputs and which steer the binary information to the output line. And this is the block diagram for multiplexer, where here the inputs are 2 power n data inputs with n control signals, and we get one output signal. And these are the types of multiplexers where the multiplexers come in multiple variations. The different types are 2 is to 1 multiplexer, 4 is to 1 multiplexer, 16 is to 1 multiplexer, and 32 is to 1 multiplexer. So here is a block diagram for 2 is to 1 multiplexer, where it involves I0, I1 and the control signal S, and we get the output signal Y. And this involves the NOT gate and 2 AND gates and 1 XOR gate. And the truth table for the same 2 is to 1 multiplexer is given here, involving the control signal and the corresponding Y value. And what are demultiplexers? A demultiplexer performs the reverse operation of the multiplexer, where it receives one input and distributes it over the several outputs. So it has only one input, n outputs, and m select inputs. So at a time, only one output line is selected by the select line, and the input is transmitted to the selected output line. So this is equivalent to the single pole multiple way switch, which is shown as in the figure here. So demultiplexers come in multiple variations. 1 is to 2 demultiplexer, 1 is to 4 demultiplexer, 1 is to 16 demultiplexer, and 1 is to 13 demultiplexer. So this multi-block diagram given here involves 1 is to 2 demultiplexer. So which has the truth table involving the enable input and the select control signals and the corresponding Y0 and Y1 output value. Thank you, students.